into this, what is a DAC and what is an ADC? All right, I'm going to probably have to move some of these pictures around. Let's give ourselves a little more room here. Get this down here. Okay. So first, it's actually easier to talk about what is a DAC first than to start into what is an ADC. So let's talk about a DAC. DAC is digital to analog. Okay? We have a way already with general purpose I/O pins to set a pin to ground and to set a pin to 3.3 volts, don't we? So far, we haven't talked about being able to set a pin, say, to 1 volt or a pin to 2 volts. We just have high, or low, right? That's it. With a DAC, depending on its resolution and all this kind of stuff, we are going to be dealing with a 12-bit resolution DAC. We have number of voltages that we can output. With a 12-bit DAC, we have 2 to the 12th different voltages we can output, with 0 being the first one, and then 4095 being the maximum voltage we can output. Okay? What, halfway? So the maximum voltage is actually 3.0 volts on this processor. Some will take the DAC all the way. Some processors go up to 3.3 volts. You can buy DACs that go minus 10 to 10 volts. Okay? Anyway, but that's another story. Our DAC goes between 0 volts and 3 volts. And then there's 4,095 different voltages in that range that we can output. Okay? So, in other words, if we think again about this DAC peripheral inside our 28379D processor, it's inside there, and you kind of draw it like this. A lot of times they call this a DAC. It's a 12-bit number, 1, 2, 3, all the bits. I'm not going to probably get enough here. But that 12-bit number is what is making the decision to the DAC what voltage to output. Okay? And so, the range is 0 to 4095. And 0, when you write 0 to the DAC, by the integer 0, you're telling it to output 0 volts. When you write 4095, you're telling it, well, plus or minus half a resolution. Sorry, now let's erase that. Erase. You're telling it to give out approximately really close to 3 volts. Maybe a half a resolution lower than that. Okay? But we're just going to assume 4095 is 3 volts. Okay? Just to make our lives a little easier. But then, of course, in between there, we can set a number of other voltages, right? Not any voltage, but a number of them, right? What can we do? Every step. So if we output 1 to the integer 1 to the DAC, that's telling it to output 3.0 divided by 4095. Do you agree with that? That's the minimum voltage you can output. 0, of course. And then the next step is our resolution, right? 3 volts divided by 4095. Then the next one would be 2 times that resolution, 3 times that resolution. See how that works? So you've got your integer number times the 3.0 volts divided by our resolution for our number of integers, 1 minus 1, and that equals the voltage that we're outputting, right? You see that ratio? So if I want to output 1.5 volts or really close to 1.5 volts, I go halfway up, don't I? So I would write to the DAC the integer 2048. Okay? And then any voltage in between there, all right? Now, we're going to make your lives a little bit easier with the DAC. The DAC, we're actually going to give you, well, I take it back. That's right. You're going to have to put in the resolution. So we're going to create these functions called outDAC, or DAC out, or something like that, right? And what it does is it takes that outDAC function that you're going to see in lab, takes a well, yeah, just one second. All right, I'm getting a little ahead of myself, aren't I? So this out DAC function that we're going to be using is not until next lab, lab 4. We're not going to be using this in lab 3. So sorry, a little bit ahead of the game. But anyway, all we're dealing with in your homework number 2 is the analog input. So I'm jumping ahead a little bit with talking about this DAC, but it helps to talk about that first. All right, so but you'll see that we're going to write a function that, given a voltage, given a number between 0 and 3 volts, we can scale that, right, to a number between 0 and 4095. And then that is the value that's written to this DAC peripheral. Okay, and then the DAC outputs a voltage. And all it really is, you could look it up, a DAC is really just an op-amp circuit. And you guys probably don't remember all your op-amp stuff, but we know we have, oops, sorry, we have positive on the bottom side. Draw, erase. So what happens is it's just an op-amp circuit, draw, with minus plus. We've got a feedback resistor. And again, this is all internal. You would not be creating an op-amp circuit. But all that happens is with a 12-bit, and I'm not going to do this, let's just do a 4-bit, you have a voltage coming in here that has a switch. So this is actually the voltage, half the voltage, so 1.5 volts is right here. Okay? Then the next summing junction, which also has a switch, has half of that, 1.5 divided by 2 coming in there. And it sums up the next, another switch, and this is 1.5 divided by 4. You see what I'm doing? And I keep on summing all the way, so we'd have all these. And so the trick, actually, for the folks making a DAC, for Texas Instruments, whoever makes a DAC chip, is to get all these resistances to the right values precisely. So they call it, they laser trim these resistors they talk about to get it super precise and super linear. Okay? But anyway, the number, right? This DAC number right here, the 12-bit number, the ones and zeros, right? If this guy is 1 way out here, remember, what is our biggest number? This is an unsigned number, right? So this, because we're just going from 0 to 4095. 4095 is 12 ones. Do you agree with that? A bunch of zeros on the left-hand side, right? Because we've got to store it in a 16-bit integer. But the 12 bits are all 1 when we're at 4095. And to output our 3 volts, when we do that, whenever a bit is 1, this switch is closed. And do you see that? So that's 1.5 plus 0.75 plus 0.375 plus 0.1875 or whatever it is, 1825. See what I'm doing? You sum up all those voltages, and then it would be outputting 3 volts, wouldn't it? When all those are summed. If we go and change that voltage and we set maybe this guy to 0, then this switch is no longer closed, it's open, so we're just summing 1.5 plus then 0.375. We're not adding in the 0.75. So it's going to be a smaller voltage than 3 volts. Kind of get that? We don't need to know this totally. We don't have to understand this perfectly. But these bits of the DAC number are deciding what voltages are going into the op-amp to get summed up. And then that produces a different voltage that goes out to the world. Why do we need a different voltage going out to the world? We love our headphones, don't we? I guess it's all wireless now. We love speakers to make noise for us, right? That's what's happening. These DACs, right? Inside your iPhone or whatever, there's a DAC that's outputting to a speaker that's making all your noise. Output to an amplifier, and then that amplifier drives current into your speaker. So we love our analog signals to produce that. Now there is digital, obviously MP3 is all digital data and all that kind of stuff, but still somewhere it's got to become analog to drive those speakers. Right? Somewhere in that mix. So anyway, that's one way. But we can drive motors with DACs. There's amplifiers that take voltage in instead of PWM in. So a lot of different things out there that we can use for DACs. So drive a different voltage. A lot more data, isn't there, in a DAC signal than just a high and a low, isn't there? There's 4,096 different signals, isn't there? in there. So we got more that we communicate with. Good. Okay, so great. That's the DAC. Now let's go into the ADC. Because actually in an ADC, at least a Successive Approximation Register ADC, there is a DAC inside of it. So that's why I like to start with that one first. Let me, again, give myself some room here. Okay, so this again, I do not want you to understand all the details of an ADC. I know I don't understand all the details, but I want to give you the really reason I want you to see what's going on inside the ADC is for you to realize that it's not immediate. When you tell an ADC to convert, it's not done, you know, a couple nanoseconds later. It's done half of a maybe more like a microsecond later, not a nanosecond. So it's not immediate. So anyway, let's think about that. All right, so what's inside a ADC is the following. And, you know, they got diagrams like this in, well, here's kind of a diagram that TI gives us in this one right here in the data sheet. Okay? There's multiple inputs. Then there's this sample and hold circuit. And then finally, there's the converter. Okay? And so that's what I want. Oh, my watch is stuck to that. That's what I want to explain. What's going on in here? Okay? Especially in the converter down in here. All right. So as I said, we've got, now we're going to draw it the other way. We got our 28379D processor. And inside this, we'll draw it the other way, is the ADC unit. And actually there's 4 of them. There's an ADC A, ADC B, C, and D in this processor. And probably a little more realistic, let's erase this. Let's draw this line a little bit bigger here. Give me some more room. Draw. All right, so let's open this up a little bit more. Okay, before this is, as it showed there, is the sample and hold, where I'll explain what that does. And then there's a multiplexer. So there's only one wire, one channel that can go into this sample and hold at a time, but there are multiple channels, multiple pins that come into this from the world. Okay, and they're called ADC in A0, ADC in A1, A2, A3, A4, okay? There's quite a number of them, okay? What has to happen first is a decision has to be made, which channel do we want to sample at this moment in time? So only one of these channels can go into the ADC unit at a time. So let's just say we've selected ADC in 0. So it's the one that's switched in there. Okay? So let's, for our example, let's say that's 1.2 volts that's coming into the ADC, that pin. There could be different voltages coming into the other channels. Okay? Just so you know, different sensors. You know, there's a lot of sensors that give out an analog voltage. The little photoresistor you're working with in homework 2, analog voltage. The joystick that you just took right here, if you didn't get one after class. Joystick this one gives an analog voltage. Okay. So that voltage comes through here. Now, again, this conversion is not immediate. So this sample and hold circuit, you kind of think what it does is, and let's draw this again. Let's go here and erase. This sample and hold is really a switch. Again, all these switches, which are usually transistors, right? There's a switch here that most of the time this switch is closed, allowing the voltage that you want to sample, whatever that ADC voltage is, to come in into the sample and hold. But when you tell it to convert, that switch opens up, and the job of this sample and hold is to hold the voltage at that value until the conversion is done. Does that kind of make some sense? Because that conversion takes some time. Now, it's really fast, but it does take some time. So that's what this sample and hold is. And then, again, we don't worry about that too much. We just know that it holds it at the right voltage. So in other words, we've told, boom, the ADC to convert. This switch opens up, and it's holding the voltage at 1.2 volts right now, because that was the voltage coming in on the ADC in a 0 pin. Okay, so great. Boom, you tell it to sample. It holds it, and then it starts converting. Okay, and how does the conversion work? This is kind of fun. So what we have inside the ADC is, as I said, a DAC. And it's a 12-bit DAC also, making this a 12-bit ADC, and I'll explain. This type of ADC is called a Successive Approximation Register, if you're interested. These are the fastest ADCs. There's a number of other style of ADCs that are usually a little slower, but these are probably the most popular used ADCs because they're so fast. All right, so we've got this 12-bit DAC. Oh, don't do that, Dan. Okay, let's think about those bits. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, bit 0, bit 1, blah, 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 all the way up to bit 11. All right. Now, just like we talked, this DAC, what does it do? Its output voltage goes into what's called an analog comparator. So this is just a comparator. Okay, and its job is just to tell the ADC if the voltage coming on the top port of the comparator is larger than the voltage coming in the bottom port. There's 2 ports in this comparator. And so see, the voltage, our 1.2 volts, comes into this comparator. Okay? And let's think about what it does. So this gives us just a yes or no answer. Is it higher or is it not higher? Okay? So let's think about that. So remember, if bit 11 is set for our DAC, that's up here. That means all the other switches are open. This is the only one closed, and we're outputting 1.5 volts. If this bit is set, we're also outputting 0.75 volts. The next one, we're also outputting to the DAC an extra part, 0.375. So, okay, let's think what happens here. So let's erase those 2 for now. All right. So when we tell it to convert, what happens is, and this is, once it starts converting, this happens in X amount of bits. So it does 12 steps with these 12 bits. So what it does first is it sets bit 11 to 1 and all the rest of the bits to 0. So what that means is coming out of the DAC is 1.5 volts. Now this is all internal to the chip, right? We cannot see this voltage on our pins. This DAC is just internal to the ADC. Okay? So this DAC, it's set to 1.5 volts, and we come down the comparator, and you know, there's a little bit of time here. So that DAC gets set to the voltage, and so there's a little time that it has to delay to see when the comparator actually gives the right answer. And so what's the answer? We've got 1.5 coming in here, and we've got 1.2 volts coming in here. So the answer is yes, 1.5 is greater than 1.2. So if the answer is yes in the way I set this up, that means we should not set bit 11. Do you agree with that? 1.5, that component, is not in this signal. If the voltage coming in was greater than 1.5, then we do need that bit set. Okay, so the ADC converter would set that to 0. Erase that. And we make this bit 0. Okay, so then it marches to the next bit. And it sets this guy. What voltage is the DAC outputting now? With that one set, all the rest of them 0. What do you think? It's 3 volts divided by 4. Do you see that? That's the next bit down. Okay, because this was 3 volts divided by 2, right? We love powers of 2, don't we, when we come to bits? So this is 3.0 divided by 4. Okay, so now this guy is outputting 0.75 volts. Okay, and so now the answer is no. This voltage is not greater than this voltage. Agreed? So that bit remains set. And it goes to the next bit. All right, and it sets this one and tries. Well, what's 0.75 plus 0.375? That's 0.1 something, right? What is that? Anybody got a calculator quick? 1.25, is that what it is? Great. Thank you. So now, what we are outputting right here on the DAC is is it 1.25? Okay, that's probably right. 1.25. All right. So again now, that voltage is greater than this. It's yes again. So that means we set that bit to 0, don't we? Because it was greater. Okay. So we've got to erase that. Now I said we. We don't set anything. This is all happening inside the ADC at a very fast rate, right? Way faster than me explaining it here. Okay? Yeah, you got your calculator out, Marius? You help me out here now. So now the next one we set, and this is 3 volts divided by 16 that we add to it, right? So that's 0.7. This would be 0.75 plus 0.1 something.
Sorry, the previous one was 1.125.
Aha. So it was 125. So then that would have said this guy would remain set here. So, because it was lower, right? It was lower than 1.2. Now we set this one, and we take 1.175 plus 0.18 something, right? And it's above 1.2, right? Yeah. So it's 1 point what? I should have had my calculator here. 2 something? No. I should have done this ahead of time. Sorry. But anyway, I believe that's bigger. And so we would erase this guy. And draw. This would be a 0. And then probably it takes a little bit, maybe 0, 0, and then finally this one would be 1, right? Once that voltage gets a little bit higher than 1.2 volts, right? And so now it's kind of down in the mix, something down here. I'm just guessing right now. And maybe something like that would cause it to happen, right? To give us the closest thing we can get to 1.2 volts. We may not be able to get it exactly at all, right? We could find that out, right? We could take, what's the closest we can get to 1.2 volts? We would take 1.2, multiply it by 4,095. Golly, draw, erase. 4,095 times 3.0. Okay, and we don't know if that's, and is that an exact integer? It's probably got a decimal point in it, doesn't it? And so we can't get exactly 1.2 volts, but we can get, within a resolution, within a half of a resolution. Our resolution is 3 volts divided by 4,095, right? Which is like 0.7 millivolts, right? So a small little voltage within that. It's getting to that voltage. All right, did that confuse you, or you got any questions about that? The main point here, it's neat to see a little bit how it works inside there, but the main thing here is that, do you see that it takes a little bit of time? So in other words, you cannot tell the ADC to convert and immediately go read its result. Okay? What you have to wait for, and that's what we're going to be doing in both your homework and in the lab next week, lab 4, is we're going to be reading the ADC result after we get an interrupt saying our conversions are done. Okay? So we're going to find that we're going to set up a PWM again. Now this PWM isn't going to drive anything in the world. All it's going to be used for is a timer. and it's going to do what's called trigger the ADC to start. And we're going to talk in just a minute about triggering these things called start of conversions. And we'll get to that. Hold on just a second. But all this timer is going to do, the PWM timer, we're going to start out with 1 millisecond. Whenever 1 millisecond of time goes by, we can set up the PWM to say, hey ADCs, start conversion. Okay? The ADC will then go through this process, and it actually may do a sequence of channels. We can set up a sequence so that it samples ADC in A0, then N1, then A2, and actually we could do it in any order. We could tell it to sample ADC in 5, and then 1, and then 4, so we can do whatever sequence we want. Okay? We'll explain that. We got to explain that sequencing. But the issue is, okay, we tell it to start, and then it goes and does its conversion. When it's done, it'll cause an interrupt to occur. Okay? And inside that interrupt, we then read the results. We read these conversions. Because the value, right, the value coming out of the DAC inside this circuit, that voltage is the closest voltage we can get to 1.2 volts. And so when we read the ADC, we're just reading that 12-bit number right there that the DAC was outputting inside the ADC unit. That is our 12-bit number. That is the converted number. Okay? All right. Now, it always gets people, because I emphasize so much this time that it takes to convert. Why do I do that? Well, do you remember when we went and read if the push buttons were pressed or not? Right? We went and read the GPIO pin to see if it was high or low. We didn't tell it, hey, go check out there to see if the switch is pressed or not. So those I/O pins are immediate. You can just read it whenever. Okay? Also, we're going to be playing around with a couple other things, like, well, the PWM too. We just write to the PWM immediately that duty cycle changes. Now, immediately is it's not actually immediately, but it's really fast. All right, we're talking. When I say really fast, we're talking nanoseconds. Okay. When we're talking kind of slow, like this ADC, we're talking microseconds. That's still really fast to us, isn't it? But to the computer, it's not. So when we're talking, hundreds of nanoseconds, then you're talking, every 100 nanoseconds, we're doing 20 instructions because our processor's 200 megahertz. 1 over 200 million is 5 nanoseconds. Okay? And so when you're talking 100 nanoseconds, or something like that, you're only talking about 20 instructions in the processor. When you get into microseconds, right, then you're talking about hundreds of instructions. Because a microsecond is 1,000 nanoseconds, isn't it? And so divided by 5, that's 200 instructions. So when you start talking in microseconds, you're wasting a lot of time if you, for example, just wait for the ADC to be done. Right? You can tell the ADC to convert, and then you can sit and watch a register bit to say when it's done. There's usually a busy bit. And you could read that busy bit. Are you busy? Are you busy? Busy means you're still converting. Are you busy? Are you busy? Are you busy? And you could do it that way. And when it finally is not busy, then you could go read the results register. But because that takes microseconds, you're wasting a lot of processing time. You should be doing other things during that. So that's why we tell it to just go convert, and then when it's done, then we can get an interrupt. It'll interrupt us just like the timer interrupts. It'll interrupt us, and then we can go read the results. Okay? All right. What always gets folks, and I understand because, again, I'm hounding on this amount of time here. Again, though, we're talking about microseconds. So we have, in time, we are going to tell the ADC to convert every 1 millisecond. So we'll call this little spike a conversion, 1 millisecond. Tell it to convert at 2 milliseconds. Tell it to convert at 3 milliseconds. Tell it, right, at 4 milliseconds. Now, that's in units of milliseconds. The conversion is done just barely after that, again in microseconds. So the conversion is finished right there, just a little bit after. Okay? So, because that is to us, and when we're talking about a millisecond sample rate, doing something every millisecond to control your car and all that kind of stuff, to control the robot. You know, people are, Dan, it takes a while for it to convert. Well, yes, in some sense. But you see, it's just maybe 4 or 5 or 10 microseconds after you told it to convert. So you can still, where does the interrupt occur? Your interrupt function is happening right here, okay? And right here, in time. So you can use that interrupt function as your every millisecond interrupt and consider that you're sampling at a millisecond. You don't have to take into account that little delay in the time when you told it to convert to when the conversion is done. Now, if you were doing an insanely fast interrupt, maybe you would, but not when we're sitting here sampling every 1,000 microseconds when the conversion takes 10 microseconds, right? That's a very small part of that full 1,000 microseconds. Do you get what I'm saying there? So we can just ignore that it took 10 microseconds for the ADCs to convert. And just assume, boom, this is where our 1 millisecond is here marching forward. Okay? Okay, good. So again, we'll keep on talking about this, but this is not our only lecture on this. We'll try to get this in your head as you're using the ADC and as you have questions. Okay, so again, now the final thing, and let's hope I have enough time, I get into this a little bit, is this idea of how do we sequence multiple signals to be converted when with one trigger source. Okay? You're going to see when you start going through homework 2, questions 3 and 4, that you have to tell the ADC unit what triggers it, in other words, what tells it to start converting, okay? And then you also have to specify what channels you want to convert. For example, for homework 2, the signals that I have wired, that I chose to wire the signals up on, are the photoresistor comes into ADC it's called ADC in A4. So, in other words, this signal right here, the 4th one, that's what's coming, the photoresistor is coming into. That's what we wired. Then automatically, or actually on my green board, how I auto-routed the wires, the 2 joystick signals coming in on 3 and 2. Okay? The reason we don't use ADC A in 0 and 1 is they have a second functionality to be used as the DAC outputs. So anyway, we don't use ADC in A0 and A1 because we're using those to output to the DAC. Anyway, that's like a MUX thing, right? We talk about that pin MUX. You would see that in the pin MUX table that it does that. Okay, so those are the 3 pins we want to sample. Okay, but just so I don't give it all to you, but I'll give you the code today anyway. But let's imagine that we're connected to ADC in A5, and then 4 and 3 and 2 or whatever. So we got a number of signals. So usually what you want to do is you want to tell all of those to convert, and then when all of them are done, get the interrupt. Okay? And then when you get that interrupt, you go and read the 4 values or the 3 values that you converted. Okay? There is, when you do get into reading about these SOCs, and when you think of SOC, think of scheduler. SOC stands for start of conversion. Okay, but think of them all in this chain like this as a way to tell the ADC unit to convert this channel, then this channel, then this channel, and then this channel, for example. You can tell it to just sample 1 if you want to. And we'll be doing that with the microphone in lab. But anyway, sometimes you'll need to tell it to sample multiple channels. Okay? And so we've got to get down some terminology here. So as I said, there are, where do I want to write this? Let's do it right here. There's three kind of labelings that we've got to get in our head when it comes to the ADC. There are these in channels. So let's just talk about ADC-C is going to be connected to our analog rate gyro. So let's talk in terms of that one. So we have ADC in C0 we could use, ADC in C1, ADC in C2, and let's just do this. It goes through, I think, C5, but let's just list off these four right here. 3. Okay, there also is an ADC C4 and ADC C5 on this processor input pin. For some reason, you're manager. I'm the manager, right? Now I say that I would like you to sample ADC in C3 first, then 1, then 2, some crazy order. Okay? With this scheduler, you could do that. Okay, and that's what I'm going to try to get to in the next 9 minutes. All right, and we'll take it up again more. But, so these are our channels. These are the pins. Okay? Then there are these things called SOCs, start of conversions. Okay? And we have SOC, as you see right here, SOC 0 through a possible SOC 15. In the homeworks, we're not going to be using all of these. And when you don't use one, this scheduling circle gets smaller. So if you decide not to use SOC 6 through 15, you can take them out of this circle and just circle the ones you're using. 0, 1, 2, 3, 4, 5, and then it jumps back to 0 when it's done with that sequence. Okay, if you don't enable an SOC, start of conversion. So this is confusing. You could do 15. Every trigger, you could do 15, actually 16 conversions. But you don't have to. Okay? So we've got these start of conversions. And then finally we have the interrupts. The interrupt numbers. And so this is where you kind of think this is due to a channel. There's ADC, ADC C1, ADC C2, ADC C3, and ADC C4. We're never going to use these other four. So this is the interrupt that occurs when we're going to always just enable ADC C1. I should say never, but in the class we'll never be using it. ADC C1 is the only interrupt source that we're going to generate. And it'll come when the last conversion is done in our sequence. That'll be our goal. Okay? So when I'm talking about an interrupt and I say ADC C1, do not think that is the interrupt that occurs when just channel 1 is converted. That's what's confusing about that labeling. But it's the one of 4 interrupts that are possibly to be generated. What's going on with this ADC? Again, I keep on coming back to 3-phase motor control. That's what this chip is designed for. And there is some of the things you read with a 3-phase motor control is not very critical in time. But when you're trying to drive the correct current through this 3-phase motor, it's actually really important to sample the current at specifically the right time and consistently doing that. And so there's ways, you'll see if you read through this, there's ways to prioritize some of these SOCs over other ones. Do not worry about that. We're going to keep the priority always 0 is the highest, 1, 2, 3, 4 in that order. So what that means is what we have to do for an SOC, we have to set up a trigger. And what we're going to do is we're going to trigger all the conversions that we want at the same time. And once the SOC is triggered, the highest priority one starts converting. And then it goes to the next one, and then to the next, and then to the next. Once it's done, the minimum priority, in order of priorities, 0, 1, 2, 3, it will go back to 0 and wait for the trigger again. Okay? So let's think about that. So I'm going to do this triggering as the priority now. Our circle is going to look like this. SOC 0, SOC 1, SOC 2, SOC 3. And this is the order that the conversions happen if we trigger them all at the same time, which is what we're going to do. Okay? If you only triggered one, well then that one will go. Okay? But we're going to trigger them all at the same time. So, what's very confusing about this is each SOC, each sequence object, right? These are sequencing, they're making the sequence happen. What you have to tell the SOC is two questions, really. Trigger. What is the trigger telling this SOC to go? Same here. This one needs to know. What is its trigger? What is its trigger? What is its trigger? Okay? Also, the second question, and what we're going to do is we're going to find in homework and in the lab, our trigger is going to be EPWM4. When its counter register equals the period register, that's a certain amount of time, boom, that will trigger that SOC. Okay? And we're going to have that trigger to be the same for all of them. EPWM4, EPWM4, the timing. Now, in this case, the EPWM4 is not being used to drive a motor or anything. It's simply being used as a timer. Okay? TI realized that they gave us 12 PWMs. They realized in a lot of situations you won't need 12, but you can use them as a timer. All right? Okay, anyway, so that's what we're doing with 4. So what happens, they all are triggered at the same time. Every millisecond we're going to set up. Every millisecond, boom, the trigger happens. And they all are triggered at the same time. So the order of sampling is SOC 0, then 1, then 2, then 3, and then stop and wait for the next trigger. Okay? Good. Last thing we got to tell it, what channels to convert. So the channel, this is where SOC 0 does not have to be channel 0. I told you the 4 we wanted to sample. We could be crazy here. We could sample ADC in C2 here. Then down here in SOC1, we could put ADC in C0 if we wanted to. Here we could put ADC in C3. Actually, we could even sample one of the channels twice if we wanted to and do an oversampling. But anyway, we could do that. And then finally, let's put ADC in C1. I don't think so that would go there. Now, is there any reason for us to do that crazy order? No, okay? But if you wanted to, you could. Make yourself sane by sampling 0 first, then 1, then 2, then 3. But just to get you understanding this, you can put it in whatever sequence you want. Okay? So that's what's confusing. Now, once it's done, the value, that 12-bit value, is put in a register called the results register. And there's a results 0, there's a results 1, come on up, results 2, and a results 3. And actually more, right? There's 4, 5, 6, all the way up to results 15. But since you only told 3 SOCs to run, 0, 1, 2, and 3, look at that. Now this is confusing, isn't it? The value of channel, the voltage coming in on pin ADC in C2 will be in results 0, won't it? The 0 here is relation to the SOC, not in relation to the channel. Okay, so this has ADC in C2's value, the voltage on that pin. And then this one has ADC in C0's value. And of course, C3's value here and C1's value here in this little way I did this little example here. Any questions about that? Probably a lot, but hopefully this gets you started much better on next question, all right? The homework questions 3 and 4. Yeah?